Hello everyone, let us continue our discussion on plane stress. We move on to coordinate transformation. So for coordinate transformation, when members of a structure are oriented in different directions, it becomes necessary to transform the stiffness relation for each member from its local coordinate system to a single global coordinate system selected for the entire structure. So we have to take note that the member stiffness relations are expressed in the global coordinate system and then combined to establish the relations, the stiffness relation for the whole structure. So in this section, we are going to consider the transformation of member end forces and member end displacement from local to global coordinate system and from global to local coordinate system. So to start with, let us try to transform global to local coordinate system. So let us consider this figure. So we have here a figure. Let us consider the member M of the plane truss. So as shown in our figure, the orientation of member M is relative to the global X and Y coordinate system, and it's defined by an angle theta. So we have here an angle theta. It is measured in a counterclockwise direction from positive direction of the global x-axis to the positive direction of the local x-axis. So we have to recall that the stiffness matrix K that was derived in our previous discussion relates member end forces Q and end displacement as U described with reference to the local XY coordinate system of the member as shown in the figure. So let us consider this figure. So we have figure B and we have figure C. For figure B, this is an illustration showing the member end forces and member end displacement in the local coordinate system. Of course, we have isolated our member M from our previous plane truss that we have shown a while ago. So we have established now, we have illustrated here our member end forces in the local coordinate system. It is denoted by Q. And of course, we have also illustrated our member end displacement in the local coordinate system. So if you're going to observe the position of the member end forces and the position of the member end displacement is parallel with the position of our local coordinate system. So we have now established our member end forces in the local coordinate system in our plane truss. So figure C now illustrates our member end forces and member end displacement in the global coordinate system. So we have to take note that member end forces in the global coordinate system is denoted by F, capital letter F, and member end displacement in the global coordinate system is denoted by small letter V to represent that this is end displacement in the global coordinate system. We have to observe that similar with our member end forces and member end displacement in the local coordinate system, there are 4 local end forces and local end displacements. Similarly, in the global coordinate system, there are also 4 member end forces in the global coordinate system and 4 member end displacement in the global coordinate system. So if we're going to observe the position of our member end forces and member end displacement in the global coordinate system, it is parallel to the position of our global coordinate system. So we have identified the position of the member end forces and the position of member end displacement in the global coordinate system, 2 member end forces at the beginning of the member and 2 member end displacement at the beginning of the member. And there will also be 2 member end forces at the end of the member, and there will also be 2 member end displacement at the end of the member. So with this, we can have, if we're going to compare our figure, if we compare figure B from figure C, we can observe that our local coordinate system would be equal to the components of the global coordinate system. Meaning to say, for example, we're going now to transform global coordinate system to local coordinate system. So if you're going to start with Q1, so for Q sub 1, that would be equal to the components of the end forces in the global coordinate system. So for example, F sub 1, the component for this is F1 cosine theta and F1 sine theta. So meaning to say Q1 is equal to F sub 1 cosine theta plus F sub 2 sine theta. So for this one, for F sub 2, this is our F sub 2. The components for this, you have F sub 2 sine theta and F sub 2 cosine theta. So in other words, for Q1, this is equal to the horizontal components of F1 and F sub 2, and that would be equal to F1 cosine theta plus F2 sine theta. For Q sub 2, that will be equal to the vertical components of F1 and F sub 2, and that would be equal to F1 sine theta plus, this would be negative of course because it is going downward, negative F1 sine theta, and we have positive F2 cosine theta. Similar procedure for Q sub 3, so this will also be equal to Q sub 3 is equal to F sub 3 cosine theta and plus F sub 4 sine theta. And for Q sub 4, that is equal to negative F sub 3 sine theta plus F sub 4 cosine theta. So we just derive the equations for transforming global coordinate system to local coordinate system. So in other words, if you're going to have the equations, of course, this is now the equations that we have identified a while ago. So similarly, if you're going to write that in matrix form, so you can have for member 1, for a member, this would be in matrix form. If you're going to transform global coordinate system to local coordinate system, so for each member, there would be 4 member end forces. So this would be equal to Q1, Q2, Q3, Q4 equal to T. This is now your transformation matrix actually. So the transformation matrix is equal to this components, to these elements. Actually, these are the taken from our equations, and this will be multiplied to member and forces in the global coordinate system. So this is the equation that you're going to use if we're going to transform global to local coordinate system for each member. So for every member, you're going to use this equation to transform global coordinate system to local coordinate system. So this can be expressed as Q is equal to T times F, where T, of course, Q is our member and forces in the local coordinate system, which is equal to transformation matrix multiplied to member and forces in the global coordinate system. Of course, our T is the transformation matrix, which is equal to this form in these elements. How do we obtain the value for cosine theta and sine theta? So this is the equation. So for cosine theta, that would be x sub e minus x sub b all over L, or that can be equal to x sub e minus x sub b all over the square root of x sub e minus x sub b squared plus y sub e minus y sub b squared. For this one, for cosine theta, this formula is being used for member in horizontal direction. So if the member is in horizontal direction, you have this equation, x sub e minus x sub b all over L. So what is the value for x sub e? x of b, and the value for L. X of e refers to, this one refers now to the dimension. If you're going to have x of e, this is the dimension of the member from the end of the member, from the origin towards the end of the member. So x of e, take note that this is the dimension from the origin towards the end of the member. X of b is the dimension from the origin towards the beginning of the member. Or basically, we can say that x of e is equal to the distance. The distance from the origin towards the end of the member. X of b is the distance from the origin towards the beginning of the member. L refers to the length of the member. When to use this one? You're going to use this one. This one you can use if the member is in horizontal direction. This one can be used if the member is in an inclined position. If you're going to have an inclined position of the member, so you're going to resolve you're using this equation so that you can get the length along the horizontal direction for our member. Then sine theta. For sine theta, y sub e minus y sub b all over L, or equal to y sub e minus y sub b all over the square root of x of b minus x of e minus x of b squared plus y sub e minus y sub b squared. When to use this one? This can be used if the member is in a vertical direction. How about this one? This can be used if the member is in an inclined position, and of course you're going to get the x component, the y component rather, for your member. You're going to use this equation. So what is y sub e and y sub b? Y sub e is the distance from the origin of the truss towards the end of the member, and y sub b from the origin of the truss towards the beginning of the member. Of course, L refers to the length of the member in a vertical direction. So this one is used if if the position of the member is in an inclined position, so you're going to get the y component for your member. So that is, after you have obtained the value for cosine theta and sine theta, you simply have to substitute to this transformation matrix equation. So what is the value for cosine theta, sine theta? Simply have to substitute so that they can have the elements for this matrix form.